That's our next section. That's what we're starting right now, inverse functions. So first off, what is an inverse function? A lot of different things that we can talk about when we say inverse functions. I'm just going to kind of keep it really simple right this second. So basically, informally, we could say an inverse function will undo its partner. So if you have two functions, that's what we have to talk about when we're dealing with inverses. We have two functions and they are inverses of each other. We like to say that they undo each other. So for example, we could have some really simple functions like these two right here, f of x, which is x plus 4. So it's taking our input value and adding 4 to it. Pretty simple function. And then g of x is x minus 4. It's, again, taking an input value and it's just removing 4. It's taking away 4 from it. So these functions would kind of undo each other. So if you put in 2 in for the first one, 2 plus 4 is 6. And then I take 6 into the other one. 6 minus 4 is 2. So one of them changed a 2 into a 6, and then the other one changed that 6 right back into a 2. So you can kind of maybe see that visually right here, that if I put 2 into f of x, I get 6. And then if I put 6 into g of x, well, I get 2. So they kind of undo each other. And also just in terms of the equations that you see for the functions, they're kind of doing the opposite thing. This one is adding 4, this one's subtracting 4. And that's it. That's all the functions are doing, and they're opposites. There are some more formal definitions of inverse functions. I mean, technically this should work with any number, not just with 2 and 6. And this does work with any number. We could kind of go through it. We could just pick something and say 0. If I put in 0, I get 4. And then I put in 4, I get 0. It kind of undid it, right? Took what the other one did and it just kind of did the opposite. But that's not really the way that we decide if two functions are inverses, because there are some functions that are kind of inverses for part but don't work all the way, and there's some that work for specific numbers but not all numbers. There are other ways that we can decide if two functions are inverses, and we'll get into that in a little bit. These ones will always undo each other. They would be considered inverses. Before we can kind of get into this of what functions are, if the two functions are inverses or solving for an inverse, we need to be able to decide whether a function is one-to-one. So one-to-one is a special characteristic of functions, and it's said this way. So a function is one-to-one if and only if for every input there's exactly one output, and for every output, there's exactly one input. So on a mapping, it might look that every number only goes to one number. And so every number in the input is only related to one output. That's just the function notate. That's just the definition of a function, right? That every input only goes with one output. The second piece is what makes it one-to-one. It's saying that every output only has one input number that goes to it. So if you look at this mapping, every number in the output column is only related to one input. There's no output that has two different values going into it, right? So if we look at -9 down here, the only input that's giving us -9 is this one. And that's true for all of them. They only have one input value that's assigned to it. That's what we call being one-to-one. Now, formally and in strict mathematical language, we might say something like what's written down here at the bottom. For any x1 and x2, those are just generic x values, different ones, in the domain, if f of x1 is equal to f of x2, that can only be true if the two values are the same, if x1 and x2 are the same. So the outputs are only going to be equal if the inputs were equal to begin with. That's guaranteeing that every output value that's different is that only goes with one input value. It's kind of a strict definition, but it allows us to show whether a function is one-to-one using some algebra. It's actually a useful thing to do. So we'll kind of see how to use algebra to show if a function is one-to-one. So I was saying there's one way to show a function is one-to-one, and that's with algebra. So we can show that two functions are equal with different inputs means that those inputs have to be equal to one another. It's a pretty simple process. We'll see how that works in a minute. And we can use something called the horizontal line test. So we use the vertical line test to see if it's a function, and we use the horizontal line test to see if it's one-to-one. It works the same way as the vertical line test. If you can draw horizontal lines anywhere on the graph and you only hit one point, then we say it passes the horizontal line test and the function is one-to-one. If you draw horizontal lines anywhere and it hits multiple times, that means that it would fail the horizontal line test, because that would represent multiple points that have the same output but different inputs that gave us it. So it would not be one-to-one. We'll go over both of these things in just a minute. So let's first look at this function right here and just show that it is in fact a one-to-one function. So we have f of x equals 2x minus 5. And we're going to show that that is one-to-one. If I can get this out of my way. Okay. So what I need to show is that if I put in two different values, so some people use the x1 and x2, and some people just use a and b. I'm going to use a and b for this one. So I'm going to show that if f of a equals f of b, so two different inputs, if those outputs are equal, that's going to have to mean that a is equal to b. So the easy way I do this is I figure out what f of a is. Well, f of a just means I plug in an a where the x is. So this becomes 2a minus 5. And then for f of b, I'm just going to plug in a b here, 2b minus 5. And then I need to arrive at a conclusion that a equals b from this equation. Well, that's pretty easy. I can just cancel everything out here that's not the a and b, and I'll be left with a equals b. So I just add 5 to both sides. Gets rid of that. So I get, well, 2a equals 2b. And then I just divide both sides by 2, which I'm allowed to do that. So I get that a equals b. So I was able to show that by setting f of a equal to f of b, I was able to show that meant that a had to be equal to b. So therefore, this function is one-to-one. It passes this algebraic test for one-to-one. Instead of a and b, some people like to write x1 and x2. It's just a matter of showing that they're the same, show that x1 and x2 are equal rather than a and b. I like a and b, but it doesn't really matter. Both methods are valid. So that was showing they were one-to-one. I want to show an example of them not being one-to-one also. So let me clear those. Okay. Struggling with my technology. Okay, so let's look at this equation and let's show that these are not one-to-one. The not one-to-one is sometimes a little trickier than showing that they're one-to-one. So again, same idea. I'm going to start with f of a equals f of b, and I'm going to try to show that that means that a has to be equal to b. So f of a is just taking a, plugging it in for x. So that becomes a squared minus 5 equals f of b. Same idea, plug in b squared minus 5. Okay, so again, I can start canceling some things out. Just like the last one, I'll add 5 to get rid of those 5s. And then I'm at a squared equals b squared. Okay, so here's where we're running into a bit of a problem. Squaring is a particular operation that causes issues with this, because if I put in a negative or a positive, I might get the same thing. And whenever we're solving an equation using square roots, we have to remember that we get a principal root, which is positive, but we also get a negative root. So when I try to show that a equals b by taking the square root here, I actually get positive or negative a is equal to positive or negative b. And in this case, this shows that they're actually not one-to-one. Because I could have, for instance, I could have positive 2 and negative 2. They're going to have the same value, but one will be positive and one will be negative, and they'll both work out in my original equation. If I plug in 2 here, I get 4 minus 5, which is negative 1. But if I plug in negative 2, I'll get the same output, because that squaring operation is an issue. It turns all numbers into positive numbers when we square it. So we'll get the same output regardless of whether we plugged in a negative or a positive value. And so in this case, this shows that these are actually not one-to-one, because I wasn't able to just arrive at A is equal to B. So this is not one-to-one. If we were thinking about the general shape of this graph, this is a parabola, right? X squared is our leading coefficient. We end up with a parabola. We could just look at that quickly and say, nope, fails the horizontal line test. Definitely not going to work, right? So horizontal line test might be the fastest way to do it, but you do need to know how to do it algebraically as well, because you might not know what the graph of a particular function looks like without kind of working it. We're working with that function before.
Wait, so the reason why it can't be one-to-one is because you didn't just get A to B, but we
Yeah, I
got
wasn't
A.
able to just get A equals B at the end. Because of the way square root works, whenever you're using the square root operation when you're solving, you have to consider all possible roots, which includes the positive root and the negative root. So in this case, when I square rooted both of these, I got positive negative A equals positive negative B. So as long as they have the same value, like a 2 or a 3, it doesn't matter if they were positive or negative, they're going to give us the same output. So that's a problem, because that's showing us that we get the same output value, the same y coordinate at 2 different x coordinates. So that's what the horizontal line test is showing us right here as well. And we'll do horizontal line tests on the next one.
All right, thank you.
Yeah, no problem. Please feel free to keep asking questions if they come up, guys. Yeah, next we're going to talk about horizontal line test. So just like vertical line test, it works very similarly. It's kind of the easy way to do it. You can graph things super quickly. Desmos is going to be a useful tool here. We can just kind of quickly visualize a graph using Desmos if we need to. Here we've got another graph. Looks like a parabola. Do you think this graph's going to pass the horizontal line test?
No.
Seeing some head shaking, heard a no. It doesn't, right? No. Why does this not pass the horizontal line test?
If you put a line horizontally across the graph, it would reach 2 points.
But what if I do something like draw my horizontal line here? Doesn't only touch it once? Go ahead.
It would have to be throughout the whole graph.
Sure, yeah. This is one place that I could draw my horizontal line, right? That doesn't prove.
Not straight.
You're right. I didn't do a good job there. But technically, you could imagine where I draw a horizontal line that only touches the vertex, right? That's kind of what I was going for there. So just because I can draw one line that hits the graph only once doesn't mean it passes it, though, and you're saying that. So there are any number of places that I could draw a horizontal line where it actually will hit twice. And so if there exists only one line that hits twice, that means it's going to fail the test, and so it won't be one-to-one. This is still a function. It would pass the vertical line test because anywhere we draw a vertical line here, it hits only once, but it's not one-to-one. Now, why do we really care about this? There are reasons. We'll get into it. Why do we care if a function is one-to-one? So we care because a function is only going to have an inverse function if it is one-to-one. So that's kind of an important reason. If we want a function in an inverse, those functions have to be one-to-one functions, otherwise they won't work. And so we could look at, I'm going to go back really quick. We could look at an equation like a very simple equation, f of x equals x squared, our basic parent function for parabolas, right? You know, it's going to just look something like this. So we know it doesn't pass the horizontal line test. So this function doesn't have an inverse, which is weird because wouldn't you think, you know, squaring, the opposite of squaring is taking the square root. Wouldn't you think if you had a function like this, it would be the inverse? Right? You're like, well, why isn't this the inverse? Squaring and square rooting are the opposites. They should undo each other, right? Like if I plug in a 4 here, it's going to give me 16, right? It would go to 16. And then if I plug in 16 here, square root of 16 is 4, right? Works perfectly. It undoes it. So why aren't these inverses? They're not inverses because they don't work for all numbers. This worked in this case, and it's going to work for a lot of examples. But if I put in, let's just say -2, -2 squared is 4, so that's fine. But when I plug in 4 into this one, the square root of 4 is just 2. It doesn't give me the negative back, right? So it doesn't work with some of the possible inputs for this function. It doesn't get me back to it. And I know just before I was really harping on when you take the square root, you have to consider both roots, the positive root and the negative root. That's true only when we're solving. If you're solving, you have to consider both roots. But if you're evaluating, if you're plugging a number in and just evaluating, you only consider the positive root. So that's a weird distinction that people tend to get caught up on. Now, technically, it is true that the square root of 4 could be a negative, and if we were solving, we would need to consider that. But if you're just evaluating, plugging it in, we don't consider it. That's just kind of a definition of the square root as an operation that we need to think about when we're doing these. So these aren't inverses, even though they sort of work like inverses a lot of the times. They're not technically inverses. And we'll see there are a lot of functions that exist like this. They work sometimes, but not all the time, so we don't consider them inverses. All right, so which of these two functions that we have graphed right here, which one is going to have an inverse? We'll call the one on the left number 1 and the one on the right number 2. So just type in a 1 or a 2. Which one will have an inverse? I'm seeing a lot of 2s, and of course, I'm assuming everyone's seeing, because we don't have an equation here, I'm assuming everyone's just looking and doing the horizontal line test kind of in their head, right? First one fails the horizontal line test. We can draw a bunch of horizontal lines through here that would hit multiple times, whereas this one, even though it's a weird graph, there's nowhere that I can draw my horizontal line that's actually going to hit once. This is some sort of irrational function. And it's got some asymptotes, but it doesn't actually fail the horizontal line test. So this one will have an inverse. All right. Okay, so here's kind of a formal definition of an inverse, and this is the one that we're going to be using. So two functions, f and g, are inverses. And this is where we're using composition. So if f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f. Basically, what we need to understand here is if we do the composition both ways, and we're able to simplify it to just be x only, then we're good. These are going to be inverses. So that's the way we'll test them algebraically. We'll just be able to plug the compositions together, do a little algebra to simplify, and as long as they simplify just to be x for both cases, then we'll say that they're inverse functions. Okay. So there's some notation that goes with inverses that we need to understand. So for a function f of x, we write the inverse of that function like this. We write f, and it looks like a -1 exponent, but this is not an exponent. This is just the symbology that we use to represent the inverse. So this means the -1 signifies that it's the inverse, it's not an exponent. So if you have a function f of x and you want to talk about the inverse of that function, we'll use this notation. The same would apply if you have g of x, then the inverse of g would be g inverse, g -1 right there. So that -1, it's a confusing thing because people read it like an exponent because it looks like an exponent, but we need to know that that just means the inverse of a function. All right, so let's show that these two are inverses. So again, all that really means is we're going to want to show that f of g of x is equal to x and g of f of x is equal to x. So we'll want to do both of these compositions and make sure they both simplify to just be x. All right, so for the first one, I'll do f of g of x. So f of this. All right, this is our g of x function. I just put it as an input into x. All right, so x is just x plus 4. So again, in place of the x, we're replacing it with the g of x function, which is x minus 4. There's nothing I can really do with these parentheses. There's no operations in here that I need to take care of. There's no exponent. There's nothing to distribute. So parentheses are just there to kind of contain my input for right now. But I have a -4 and a +4. Those are going to cancel out, and I'm left with just x. This one was pretty easy to see that these just cancel out, and we're left with x. So it works for that way. It worked for our first composition, and we just need to make sure that it works both ways, because sometimes they'll work one way but not work the other, so therefore they're not inverses. So now we need to show that g of f of x, so f of x is x plus 4. This is my function f of x. And g of x is simply x minus 4. So where the x is, I need to put my function f of x. So I need to put in x plus 4. And again, just like the other one, there's no simplifying that can take place with these parentheses, so they might as well not be there. They're sort of containing my input. I have a +4 and a -4, which cancel out, leaving us with just x. So in this case, we were able to show that for both compositions, we just got x, so these are inverse functions. So they have different names. One of them is called g of x and one of them is called f of x. So it's not clear that they're inverses since the goal was to test whether they're inverses. We didn't call one of them the inverse of the other one, but you might say something like that g of x is equal to f inverse of x. That g of x is the inverse of function f. Or you could go the other way. You could say that f of x is the inverse of g of x. However way we wanted to say it, they kind of mean the same thing. They're inverses of each other. So I'll leave this here for a minute. We're going to do another example of showing that we have inverse functions. And these were pretty easy functions, so it was pretty easy to do the composition and show. As the functions themselves get more complicated, it'll obviously be a bit more complicated to do the composition, and therefore it'll be more complicated to show this, but same idea. All right, so I'm going to go ahead and clear this. I am recording this, so I'll post this up later, but I'm going to clear what I have right here. Okay, so we've got these two functions. One thing to keep in mind when you're looking at two functions, if you're trying to test whether they're inverses, something to think about is what operations are actually taking place in the two functions. You should see the opposite operations taking place in the functions. So here I have a -4, and in the other function I have a +4. And here I'm multiplying by 3, and in this function I'm dividing by 3. So you can see that there are sort of the opposite things taking place. So that gives me a good indication that these might be inverse functions. But the order that the operations happen are important. So it's possible that the right things are happening, but they're happening in the wrong order so that they aren't truly inverses. So you have to be careful. That's not a thing where you can just look at it and say, yeah, the opposite things are happening. These are for sure inverses. It's just kind of an indication of, okay, I'm seeing the opposite things happen, so it's likely they're inverses. Now we'll check. Okay, let's go ahead and check. And I pressed something and went to the wrong thing. Okay, now that I've done that. Okay, so we're going to show that these are inverses of each other. So we want to show that the composition both ways is going to simplify to just be x. Hopefully that's true. So I'm going to do f of h of x. So I'm going to do f of that. X plus 4 over 3. So I'm going to take my function here, and instead of the x, I'm going to plug in that. X plus 4 over 3. So again, where the x was, right, I just plugged in the other function h of x. That's what's happening there. So that's my composition function where I put h inside of f. So I need to do a little simplifying. Well, this is nice. Multiplying by 3 and dividing by 3, those things actually just cancel out. So we end up with x plus 4 minus 4. Conveniently, that's actually exactly what the other one was like. So we know that we just get x. So cool. So it worked out one way. We just need to make sure that it works out both ways. So now we're going to do h of f of x. So h of 3x minus 4. That's my function f of x. So I'm putting f of x inside of h now. So I'm going to take my function h of x, but where the x was, that's where I'm leaving myself some open parentheses to put the other function inside of it. Okay, so up on the numerator here, there's nothing to do inside these parentheses, so they might as well not be there. I'm going to kind of ignore the parentheses here. I have a minus 4 and a plus 4, which are going to go away. So we end up with 3x over 3. And the 3's cancel, so we end up with just x. So great. This one did work out. We were able to show that both of those compositions simply simplified into x. So these are inverse functions. Just like a tiny bit more complicated than the first example, added kind of an extra wrinkle to it, but the same thing is taking place. These are inverse functions. So remember how to write compositions. So there's two ways. I could write this as f of h of x. That means I put h of x inside of f. And for this one, I could write this as h of f of x. I put f inside of h in this case. Or the other way was to write it as h of f of x. These two things mean the same thing, just some slight variation in the way we can write it. This is used only because it's a little easier to write, I guess. I don't know. I don't love this notation because it's hard to visually see which function went inside the other without reading it out to yourself. I tend to prefer this one, but I want to make sure we understand it both ways. All right, we have 4 minutes. I'm going to try to do one more example of this, and then we'll kind of stop there. So I'm going to clear these. If I forget, there's been quite a few questions on different homeworks and quizzes and stuff. So I'm going to be doing office hours today as well. Just use the same office hours link that's on the Google Classroom page. So I'll just be there from 1:30 to 2 again a day if you need some help. So if you don't need to come by, don't worry about it. But if you want to, we can do some problems together. Okay, so let's go ahead and show these two functions are inverses. Again, you can look and see they are more complicated functions, so this is going to take a little bit more complicated algebra to try to simplify it down, but hopefully we can get there. So I'm going to first do g, boy oh boy. First, I'm going to do g of h of x. So I'm going to do g of 5 over x plus 2. So that's my h of x function. So I'm going to start off with my g of x, so 5 over x minus 2. And where the x was, I'm just putting in the other function, 5 over x plus 2. Okay, so here we have the plus 2 and the minus 2, again canceling, because there's nothing I can do inside those parentheses right now. So we end up with 5 over x. So I'm doing 5 divided by this fraction. So instead of dividing by a fraction, remember I can always multiply by its reciprocal. So this is really the same thing as 5 times the reciprocal of that, x over 5. And then 5s are going to cancel, and we're left with just x. So more complicated algebra is taking place there, but it did reduce to x. So we're on a good start. It worked one way. We just need to make sure it works the other way too. So now I'm doing h of this, 5 over x minus 2. So that's going to be 5 over x, which is 5 over x minus 2 plus 2. Okay, bit of a mess. Remember, instead of dividing by this fraction, I can simply multiply by the reciprocal of this. So this can turn into 5 times x minus 2 over 5 plus 2. Right, instead of dividing by this fraction, I can simply turn it into its reciprocal and change it to multiplication. 5s cancel, so we end up with x minus 2 plus 2. And the minus 2 and the plus 2 become 0, so we end up with just x. So, huzzah, inverse functions. Again, the more complicated the functions are, the more complicated the algebra is going to be to demonstrate that they are inverse functions, but the process is the same. We have to put one function inside the other, and then do it the other way, and show that they both simplify to be x. If I get anything other than x, they're not inverses. All right, I'm going to stop right there. Again, I'll be doing office hours again today, 1:30 to 2, so just drop by if you have questions on the homework so that I can kind of help you more personally there. Look at the 1.5 homework, and we'll meet again tomorrow.